Much like atomic mass is the average mass of an atom in AMU, that number on the periodic table is the average mass of the isotope of the atoms in AMU. Formula mass is the average mass of a molecule or a formula unit of a compound. So molecule and formula unit basically mean the same thing. It's just called a molecule when it's two nonmetals, when it's covalent. And it's called a formula unit when it's an ionic compound. So that would be a metal plus a nonmetal. So it's just a terminology thing, but they basically mean the same thing. The way you calculate a formula mass is you take the number of atoms of the first element in the formula times its mass, plus the number of atoms of the second element times its mass, plus the number of elements of the third atom times its mass, so on and so forth. So to be able to calculate the formula mass for these, you obviously would need to know how to put the formulas together from the name. So carbon dioxide prefix, you just use the prefix to write the formula. And when we're calculating the formula mass, you're going to go to at least 2 decimals. Sometimes your periodic table goes to more, sometimes it goes to less. If it goes to less, that's fine. But you want to go to at least 2 decimals if you are able to. So carbon dioxide, carbon is 12.01. There is 1 carbon in the formula carbon dioxide. Oxygen is 16. There are 2 oxygens in the formula. So I do basically 12.01 times 1 is 12.01. 16 times 2 is 32. Add those together. So I get 44.01 AMU as my formula mass for carbon dioxide. For calcium nitrate, the formula of calcium nitrate, you have to use the charges. Calcium's a +2, nitrate's a -3. So you need 3 nitrates to balance out the charge of the calcium. So my formula is CaNO32. And then to calculate that mass, calcium's mass is 40.078. There's 1 calcium in that formula. Nitrogen's mass is 14.01. There are 2 nitrogens. And then oxygen's mass is 16, and there are 6 oxygens. So 40.078. And then this nitrogen would be 28.02. And then 16 times 6 is 96. So you're going to add that up. And you are going to get 164.098 AMU. If you went to a different amount of decimal places, you might get a slightly different mass, but it's not really going to make much of a difference in the end. So like I said, go to at least 2. Oxygen, I'm just doing to 16 because it's very, 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 it's like 15.999. It's so close to 16, just call it 16. So the molar mass of a compound is the mass in grams of 1 mole of its molecules or formula units. So just like the molar mass of an atom was its atomic mass, 1 mole of calcium, for example, is its atomic mass in grams. So 1 mole of calcium is 40.078 grams of calcium. Same thing when we have compounds. So the molar mass of the compound is numerically equivalent to its formula mass with units of grams per mole. So if I come back to this slide for a second, if my formula mass is 44.01 AMU for carbon dioxide, my molar mass is 44.01 grams per mole. And what that means, if you remember from last chapter, is that 1 mole of carbon dioxide then would have a mass of 44.01 grams. Same thing for the calcium nitrate. The molar mass would be 164.098 grams per mole. So 1 mole of calcium nitrate has a mass of 164.098 grams. So this slide basically is what I just covered. So you, just like in chapter 2, you can use that molar mass as a conversion factor between mass and amount of a compound. So our conversion factor that we used last chapter was 1 mole is 6.02 times 10 to the 23rd atoms. But remember that number, Avogadro's number, 1 mole is just an amount of something. So the unit we were dealing with last chapter was atoms. This chapter, we're dealing with molecules and formula units. So 1 mole is equal to 6.02 times 10 to the 23rd molecules. And 1 mole is equal to 6.02 times 10 to the 23rd formula units. So like 1 mole of hydrogen, that's a bad example because it's diatomic, sorry, 1 mole of calcium is 6.02 times 10 to the 23rd atoms of calcium. 1 mole of water is 6.02 times 10 to the 23rd molecules of water. 1 mole of potassium oxide is 6.02 times 10 to the 23rd formula units of potassium oxide. So it's different terminology depending on what unit of matter you're talking about, but they all basically mean the same thing. And then, of course, 1 mole is the mass off the periodic table. So same conversion factors as last chapter. So I'm starting with 10.8 grams of carbon dioxide, and I want to go to molecules of carbon dioxide. Anytime you see mass or grams in a problem, the first thing you're going to want to do is add up the molar mass of the compound. So carbon dioxide we had already done. So we know that it's 44.01 grams per mole. So I'm going to write down what I'm given, 10.8 grams carbon dioxide. And then just like before, you immediately cancel that unit. Before you even think about what do I do next or anything like that, cancel that unit. And then my conversion factor from grams, I have to go to moles because that's what that molar mass means. 1 mole of carbon dioxide has a mass of 44.01 grams. So I'm going to put 1 mole on top and 44.01 grams on the bottom. I have to keep going because it's asking for molecules and I'm only at moles. So I'll cancel mole and then go to molecule. And then as you can see, there's molecules, right, in my conversion factor. So 1 mole is 6.02 times 10 to the 23rd molecules. So when you do that math, you should get 1.48 times 10 to the 23rd molecules. Carbon dioxide, 3 sig figs because what I was given is 3 sig figs. Remember, sig figs don't come from conversion factors. They always come from what you were given. All right, another example here. We have 325 milligrams of aspirin. I want to know how many molecules that is. So again, anytime you see grams or mass, the first thing you're going to do is add up the molar mass of the compound. So carbon's 12.01. There are 9 of it. Hydrogen is 1.01. There are 8 of them. Oxygen is 16. There are 4 of them. So when I add that up, I get 180.17 grams per mole. So again, what that means is that 1 mole would equal 180.17 grams. So I will write down what I'm given, 325 milligrams of C9H8O4. Immediately cancel milligrams on the bottom. If you look at your conversion factor, 1 mole is 180.17 grams. So the first thing I have to do then is go from milligrams to grams. So 1,000 milligrams in 1 gram. Then I can cancel grams. And here's where I would use that molar mass. So 1 mole is 180.17 grams. And then finally, I need to cancel mole. And I need to go to molecules. So it's 6.02 times 10 to the 23rd molecules. So mathematically multiply the numbers on the top together, multiply the numbers on the bottom together, divide those two numbers. You should get 1.09 times 10 to the 21st molecule C9H8O4. Okay, one more example. So we're going to kind of go the other way here. We're starting with molecules, and we're going to determine the mass of that sample. But again, like I said, if you see mass or you see grams in a problem, the first thing you're going to do is you're going to add up its molar mass. So water's H2O, hydrogen's 1.01 times 2, oxygen is 16 times 1. So 18.02 grams per mole is my molar mass of water. Write down what you're given, 3.55 times 10 to the 22nd molecules. I guess we throw H2O in there. Cancel molecule. Your only conversion factor you have for molecules is to go to mole. So 1 mole is 6.02 times 10 to the 23rd molecules. Then I got to get to mass, which is grams, so I'm going to cancel mole on the bottom. I'm going to use its molar mass, so 1 mole is 18.02 grams. So for this one, you should get 1.06 grams of water when you are done.